So let's see. Let's talk business for a second. The exam, yeah, exam 2. It is when? A week from Monday. So 2 Mondays from now is the exam. So that's 10 days. So we'll have 4 more classes, and then we'll jump right into that. As I've said all along, if you've got Easter plans and those are going to conflict with your ability to study, I'm happy to push that back to Tuesday, but you need to let me know. Okay, so let's see. If you checked out the workshop from Wednesday, you noticed it was really short. So that's because instead of writing the entire workshop just in one big sheet, I basically have made a sheet for each of the homeworks that I've given out. And so those are all under the solution guide on Blackboard. And so all that workshop data is basically now listed right by or even on the homeworks that I've been producing. Okay, so I don't know, against my own feelings, I went ahead and posted the key to the practice exams. So some of you have probably seen that. So that's there. I do advise you to, because we still haven't covered everything on the exam yet, and so don't ruin that for yourself by seeing the answer to some of these things we haven't even covered, because then it's going to be a little tougher for you to assess yourself at the level of difficulty as those problems are likely going to be. So just be smart with that. And then, we've got the office hour yesterday. I thought that was really good, really informal. We basically can sit around a conference room. It was really good. So I think that's going to work out really great. We've got another one today from 12:30 to 1:30 in the conference room. And so, is there a workshop on Sunday? No. There's no workshop on Sunday. I'm getting on a plane this evening, and so I'll be out of town until Sunday evening. Which, saddest thing in the world. I've got a board Sadie, and she was a shelter dog that spent the first year of her life, I think, just basically in kennels, right? And so she's now found her forever home, and she's been so happy. And so you can explain, I guess, to a child, hey, I'll be back on Sunday, but no, I've got to just stick her in a kennel at a boarding place and walk away, and she doesn't understand. So I'm already a little...
She'll forgive you.
So the thing about that is I can't have current students dog sit because I feel compelled to pay you, and now there's a weird dynamic there. So in the future, if you are responsible and want to dog sit and you're not my student, let me know. I'll keep that in mind. All right, so for now I need to board her. Okay, so. Let's see, we finished up carbocation. Oh, any questions about stuff? All right, so we finished up carbocation mechanisms, or at least the mechanistic information on what day? Wednesday. And so just a brief review of what we'll just often call C+ mechanisms, so carbocation mechanisms. So what we found is that in terms of regioselectivity, what could we say about them? We're gonna call the regioselectivity of a carbocation mechanism. It starts with an M. Has to do with adding a hydrogen to its buddies. Yeah. So we're just gonna say that C+ mechanisms have Markovnikov regioselectivity. And so that all has to do basically with the formation of a more stable carbocation. That tells us which regio product is possible. So we're looking for, ultimately, a more stable C+. And then we talked about the stereoselectivity. And so how would you describe the stereoselectivity of carbocation reactions? Well, they were messy, right? There were a lot of possibilities. So from the first step, the protonation, that could happen in 2 ways, from the top face or the bottom face. And then the second part, when we snap together our nucleophile with our carbocation, again, it could happen from the top face or the bottom face. And so for stereoselectivity, we'll say there's none. And so that means that we end up seeing very messy reactions. There's a lot of possible products that can form. So none, very messy. And then furthermore, and this is only going to occur when we have carbocation mechanisms, but we saw that 1-2 shifts are possible. And so that makes these things even messier. And so carbocations are basically as messy as it gets because there's a lot of possibilities in terms of stereoselectivity and then shifting carbocations that can occur. Okay, so now that we've talked about the mechanism, we're going to move on to Roman numeral 4. And so we're just going to talk about a couple of different carbocation reactions that occurs. And so the good thing, the reason that we've spent so much time talking about this mechanism is because mechanistically they're all going to go through this, right? We don't have to worry too much about the mechanism of these new reactions because they are all these type 1 carbocation mechanisms. So we'll just call this C+ reactions. And so the one that we've been using a ton of, we're not really going to talk about much because we've been doing a lot. So we're going to say that our first reaction, our first official reaction is going to be where we take a starting material such as this. And so we add it to HX. And so we've been using HX as a strong acid. So that can be chlorine or bromine or iodine. And so what we found is that in doing so, we go through a mechanism where we protonate first, and so when we protonate, essentially what we're going to do is we're going to protonate at this secondary carbon, because by doing so, we're going to be able to form this, this tertiary carbocation. And so then finally we have our X left over, and so we snap those together. Of course, now we've got a planar carbocation, and so that X can approach from either the front face or the back face. And so to show that, you can draw out all the possible products, and so we'd have two possibilities here. Or what you can do is you can say, well, we could have it approach from the front, in which case we'd end up with this product. Or we could approach from the back. And so if we were to approach from the back, what would the relationship between those two products be? How many chiral centers are there on the molecule? There's one, and so if this approaches from the front, we're going to have the X on a wedge. If it approaches from the back, we're going to have the X on a dash. And so what would the relationship between those two be? There's enantiomers, right? Because we flipped the one chiral center, and so you don't even have to draw out of the products, all the products out. You could just say this plus its enantiomer, right? That saves you a little bit of time. That's telling you that you know that you can have two possible products here, but instead of having to go through the process of drawing them out, you can just say, well, you would form this, or you could draw the other one, right? You could draw the enantiomer and then just say plus enantiomer. All right, so that tells me that you understand there are two products and you know what is going on. Okay, so the way we're going to do this, and I think the best way to categorize all these reactions, so I want you to basically start a new page in your notebook, and we're going to save this, and we're going to end up making a huge table of all the reactions, and we're going to it's going to give you an easy way to compare and contrast. Yeah?
Are the hydrogens still implied in that product?
Yep, definitely. Okay, so what we're going to do with our table is I'll draw a line here every time that I want to put an entry in our table. So we're going to make some headings first. Okay, so our headings are going to be as follows. We'll just have something that we call the reaction number. And so that's just going to be an easy way to look back in the notebook and know what we're talking about. So we'll have reaction number. Then we're going to have the electrophile and the nucleophile that we end up with on our product. All right, so in this case, our electrophile is an H, and the nucleophile is the X. Okay, so next up, we'll talk about actual reagents that we can use to undergo these reactions. So we talked about multiple reagents for this. So we can use HCl, we can use HBr, we can use HI. So there's going to be cases where there's a few different things we can use to end up with similar products. All right, then we will talk about the regioselectivity. And we talk about one, we'll talk about the other. So we'll talk about the regioselectivity, the stereoselectivity, and then finally, we will describe the mechanism type. So this is going to be a really quick, easy way for you to, if you have a question about a reaction, glance at your table, and so you'll be able to grab that information. Okay, so let's go ahead and put this on it. Let's say that we've got reaction number 1. And so what we end up with when we add an acid to a double bond is our electrophile every time is what? What do we end up with as the electrophile in our product here? It's a hydrogen, right? So we'll just say, well, in every case that we do reaction 1, we end up with an H there, right? That's our electrophile. That's what gets added. And so for our nucleophile, every time that we do it, it's what? It's X, right? It's some halogen. And so that's what we'll write. We'll just say, well, every time we do this reaction, we end up with some X, the X depending on what our reagents were. All right, so the reagents we'll be using in these reactions, you can see HCl, you can see HBr, and you can see HI. That's pretty much it, right? So anytime you see a strong acid, one of these strong halogen acids, you know that this is what we're going to go through. All right, the regioselectivity we've already described as what? It's Markovnikov. And anytime we go through a carbocation, it's going to be Markovnikov. So we simply say Markovnikov. What about the stereoselectivity? Unfortunately, there is none, right? Carbocations are messy, so we'll just say there's none, which means we're going to basically, in most cases, be able to form as many products as would be possible based on stereoselectivity. And so finally, for mechanism type, we'll just say that's C+. It's a carbocation. And so what we're going to find is ultimately we're going to end up with 3 types of mechanisms. And so we'll first do all of our carbocation mechanisms, and then we'll do our type 2 mechanisms, and then we'll do our type 3 mechanisms. And what you're going to find is a lot of this information is going to be identical. And because this information is based on this, if they have this in common, they too will have this stuff in common. So that kind of helps us simplify all this information that we're going to end up learning about the reactions. All right, so that's on a new page. We'll go back to our notes now. So definitely make sure, and if you write big, maybe you should save 2 pages for this table. We're going to end up listing, I don't know where we're going to get, but somewhere between 9 and 10 to 12 or 13 reactions total. So we'll see how we do on time. Not today. That's like through next Friday. So, all right, we have plenty of time to talk about this stuff. Okay, so we're talking about carbocation reactions, and so that's number 1, and I don't want to spend any more time on that. We've done a lot of those. So the next thing we'll do, we'll go ahead and we'll start talking about reaction number 2. And so for reaction number 2, we're going to refer to it as a hydration reaction, and furthermore, we'll call it an acid-catalyzed hydration reaction. So what do you think when you think about hydration, or when you hear hydration? Water. Yeah, and so we're definitely going to have water that's going to be an important part of this. So let's see what we'll do. Okay, so let's draw a starting material. And so in this reaction, what we're going to do is we're going to treat it with 2 things. All right, so we're going to start out. All right, so you said water, so we definitely want to make sure we have water in there. And so I say it's acid catalyzed. So what that means is we're going to have some amount of catalytic acid in there, right? So we'll also have some kind of HX, but specifically, it will be there in catalytic amounts. What does that mean? It's just there a little bit, right? And so let's say we have 1 equivalent of this starting material and 1 equivalent of water. We might have 0.05 equivalents of that. It might be 5% compared to everything else. So when we say catalytic acid, it means there's just a little bit. All right, so right off the top, if we were to add a strong acid to these 3 things, or to these other 2 things, what have we got? We've got our starting alkene, and we've got water, and we've got HX. And so when we talk about acid-base chemistry, what happens when we add a strong acid to water? We protonate the water, right? That's the definition of a strong acid. We're going to fully dissociate that acid and form hydronium. And so that's exactly what happens in this case. We're going to form H3O plus A minus. And so technically, that's the first step, but that's something we know already. We know if we mix a strong acid with water, what we've really got, we don't have any HX. I guess I should change this to X minus. What we really have is H3O and just X minus in this case. Okay, so mechanistically, what's going to happen? All right, I need to shift this down a little bit. All right, so you go down here. So really what we've got when we do this reaction is the catalytic acid is converted to hydronium. And so what we want to show is that hydronium. So we've got H3O plus here. All right, so let's think about this. We've got an alkene. And so is hydronium, what kind of acid is that? Strong or weak? It's still strong. All right, so the pKa of hydronium is going to be somewhere around, I believe, minus 1.7. So it's still a strong acid, but when we think about HCl with its pKa of like minus 5 or something, that's a much stronger acid, and so it's H3O plus that dominates this reaction. All right, so we have an alkene and a strong acid. Knowing what we know about carbocation mechanisms, what's going to happen? We're going to protonate. Just like we've always done, we're going to protonate. So where are we going to start our arrow? Double bond, like we always do. And so we're going to draw it down to our acid. We're going to deprotonate our hydronium. Okay, so what are we going to form when we protonate our double bond? What's the intermediate in one of these reactions? It's a carbocation, right? Every time it's going to be a carbocation. We are going to form water, you're right, but we have tons of water there already. All right, so what we'll do, and specifically, we've got a secondary and a tertiary carbon. And so where are we going to protonate, the secondary or the tertiary? I got it backwards. Tertiary, secondary. Yeah, we're going to follow Markovnikov's rule, right, which all carbocation reactions are going to follow. And so we'll add our proton to the secondary, which means we're going to end up with that right there. All right, so we're going to end up with this tertiary carbocation that's pretty stable. All right, so what's left? I guess we've got H2O, and we've got some X minus in this case. And so because we've used just a little bit of the acid, we've used a catalytic amount of the acid, when we look at our water, we've got lots of water. Let's say in this case, you can pretty much assume you've used 1,000,000 times more water than everything else in this reaction. So there's going to be lots and lots and lots of water floating about this reaction. But we've used a catalytic amount of acid, which means how much of this is there? Just a tiny amount. All right, so furthermore, we have two areas of electron density that we could imagine snapping to our carbocation. We've got this negatively charged X, and we've got this H2O. Now, not only do we have a lot more, and I mean a lot more of the H2O in solution, also what we can say about the H2O versus the X is that the H2O is much more nucleophilic. And so when we snap something together to our carbocation, what do you think it's going to be? Do you think it's going to be the X minus, or do you think it's going to be the H2O? H2O. Absolutely, it's going to be the H2O. What we're going to do is we're going to hydrate our carbocation. We're going to add water to our carbocation. So we'll start our arrow where? Yep, always at electrons. And we'll draw it right in there. Okay, so let's see what forms when we do so. Now, what's the hybridization of that carbocation? It's sp2. Is that planar? Does that mean we can get approach from the front or from the back? Sure, right? So that carbocation is in the plane of the board, and just like any carbocation mechanism, we're going to get approach from both the front as well as the back of that carbocation. So what we'll end up with, if we come from the front, we will push our methyl group to the back, and end up with that right there. All right, so charges. What kind of charge should we have on that structure? Is the carbon still positively charged? No, we've gotten rid of the carbocation, but where have we essentially moved the positive charge to?
The oxygen.
Yeah, now we're on the oxygen, so we've got this right there. Of course, that's not the only product we could form. We also have this plus the enantiomer that would occur if we were to attack from the back side. And so in that case, we would end up with this OH2 plus on a dash instead of a wedge. All right, so here's the one key difference between the mechanisms we've seen thus far. And so what I'd like to say is that we always want to end up with a neutral product. And so when you look at this positively charged oxygen, Josh, you got a question?
Yes. So the reason why the H2O attaches to the molecule is because simply there's more of it.
Two good reasons. There is more of it, and not only is there more of it, it is more nucleophilic. It is more hungry to basically attack that carbocation. So not only does it feel more attracted to it, there's way more of it, right? And so because of those two things, you have two things that are going to highly favor the addition of the OH. And so furthermore, let's think about this. If we were to add the X minus into here, well, how much of this HX did we start out with? We were saying 5%-ish, right? A catalytic amount. And so if we have 100% of this and 5% of this, well, how much of this product could we form where we added this X into the carbocation?
Not much.
Just 5%, right? We couldn't form any more of that product than we have of the beginning X in the first place. And so even if we did see any addition of this to here, it's just going to be a tiny amount, and it would absolutely be a minor product. And in this case, we don't even consider it because the X minus is just much less nucleophilic. So we're always going to add in the water. Water is just more nucleophilic than X minus. Okay, so if we always want to end up with a neutral product, what we've got here is, all right, so this thing right here, do you think that's going to be acidic or basic? These protons right here. Yeah, I mean, it's not going to be basic, right? So what we have is essentially something very similar to this, right? This looks very much like the hydronium, where we've got 3 things connected to oxygen, and we saw that the pKa is minus 1.7, and so this is going to be similarly acidic. And so how do you think we can most easily get to a neutral product? We can just deprotonate, right? So we can basically take one of these hydrogens away. And so when you're drawing a mechanism, you don't have to be too specific. What you can just use is a generic base. You can just use the letter B with some electrons, just indicating that it's a base that's going to donate electrons and deprotonate. And so in our last step in this case, what we want to do is deprotonate one of these protons to ultimately end up with a product that looks like that. Of course, how many products would we have? We'd have 2. So we would have this product plus the enantiomer. All right, so what functional group have we added to our alkene? We have an alcohol now, right? So by hydrating our double bond with a little bit of catalytic acid, we've been able to form an alcohol product. All right, so if we were to draw an energy diagram for this, it would look a little different than the carbocation reaction we've seen thus far. Why is that? So in this case, yeah, we've ultimately got 3 steps. So when we've been doing our carbocation mechanism, we've just had 2 steps, right? We've had the one intermediate that was the carbocation, but now we see we have an extra intermediate. Which do you think is going to be the more stable intermediate? Is it going to be the carbocation, or is it going to be the positively charged oxygen?
Positively charged oxygen.
Carbocation. You said that the carbocation is the only one that has positive charge.
What's rule number 1 in determining stability? Full shell. Which one's full shell?
Oxygen.
Oxygen. Which one's more stable?
Oxygen.
Oxygen. Okay, so if we were to draw an energy diagram for this reaction, it would look similar, but we'd essentially have an extra intermediate. And so we'd say energy, reaction, progression. And so we'll have starting material and product. And so we want to show our 2 intermediates. And so which is going to be higher in energy, carbocation or the positive oxygen? Carbocation. And so show that there and that there. So we've got C+, O+, product, starting material. And so if we were to connect these things, we'd see a reaction that looks kind of like this. And so for the hydration of a double bond, is the rate determining step still the formation of the carbocation?
Yeah.
Yeah, absolutely. We see that's going to be the highest point. So we've still got a rate determining step, and so that's why we end up considering this the same mechanism, because it's ultimately the rate determining step that is going to be how we classify the mechanisms. Okay. Importantly, why are we allowed to? Yeah, Luke.
So when you first attach your water to the structure, you have that O plus. Why would the X minus not attach to that?
To the O plus?
Yeah.
And so what you'd end up with that case would be an oxygen bonded to 4 things, right? And so furthermore, you already have this lone pair there, and so that would violate the octet rule. So we can never snap those 2 things together. Yeah.
So, if you don't have a base in the solution, you use water as the base? Or
Yeah, you could use water as the base. Anything with some electrons you can use as the base. And so to make it easier, you can just use a B with some electrons. But if you want to use water, and technically it probably would be water in this case. Yeah.
why didn't you draw the base plus the hydrogen as the product?
Well, that was going to be my next point. And so the reason that we're able to use just a catalytic amount, and so let's actually use water as the base in this case. So let's see what happens. If we use water as the base, what would that water turn into in the product? It turned into hydronium. And so why are we able to get away with just using a catalytic amount of acid? Because essentially the acid is going to be regenerated, right? And so now that we have regenerated our acid as a product, this acid gets to go all the way back over here and just kickstart another cycle of this mechanism, right? So we just need a little bit of acid because every time we do the reaction, we regenerate the acid. We put acid in, but then we get acid out as well. So we just need a little bit of that acid to make it go. Okay, so let's go ahead and add this to our table. So this will be reaction number 2. So in reaction number 2, what we've got in terms of our, all right, so what's our electrophile? Yeah, it's hydrogen again, and in any of these carbocation mechanisms, it's going to be hydrogen. So our electrophile is hydrogen. What's the product of the nucleophile end up as on our product? What functional group did we create? An alcohol. And so what we'll say is that our nucleophile at the end ends up being OH. We're able to add an OH. So I like to write the table this way because basically you have a quick, easy glance at what's going to be the product of this reaction, essentially, right? It's these two things that we're going to add to our double bond. All right, so anytime we're going to do a hydration reaction, our reagents have to include water. So what we're going to do is we'll have always H2O. And then in addition, we have to have a catalytic amount of acid, and so you can use HX. You'll also use, or see used, sulfuric acid in this case. So it doesn't have to be a halogen acid. It really can be any strong acid, but these are the really common ones that you'll see used. So anytime you have water plus some catalytic amount of strong acid, you're going to know immediately that you're going to undergo a hydration reaction. All right. Regioselectivity. What would you call it? Markovnikov, right? We're going through a carbocation intermediate, and so the rate determining step tells us that we're going to form the product that results from the more stable carbocation. And so again, we're going to call this the Markovnikov regioselectivity. Here's a good thing about this Markovnikov, that we're only going to learn one reaction the entire next week that has anti-Markovnikov. So for the most part, everything is Markovnikov, but we do need to classify what we're talking about here. Stereoselectivity, is it good or bad? In terms of obtaining the fewest products, is it good or bad? It's bad, and it's bad because there is no stereoselectivity, right? So we're going to end up with lots of possible stereoisomers. So set addition can occur, or anti-addition can occur, and furthermore, both of those can occur from either side. So lots of possible products. And then finally, our mechanism type, we would say carbocation, C+. And so you can see now, well, reaction 1, reaction 2, they're both the same type of mechanism, and so we see that very similarly, they have the same regiochemistry, and they have the same stereochemistry as well. All right, I gotta make a decision on whether I'm gonna leave something out or not. I'm gonna leave it out. Okay, easy decision. So, we're just gonna call that good for carbocation mechanisms for right now. We're gonna go ahead and head right into our type 2 mechanism. And fortunately, we're not going to have to spend like 2 full days of lecture talking about the mechanism, because everything from here on out is quite a bit easier. All right, so Roman numeral 5, is that right? Yeah, okay. Roman numeral 5, we will call mechanism type 2. And so the thing that I left out from the type 1 reactions is something where if we have enough time, we can quickly come back and look at it on Friday of next week. It's a very simple derivative of what we've already seen. Okay, so what we will nickname mechanism type 2, we're going to call it halonium. All right, so we've had carbocation mechanisms, and now we're going to have halonium mechanisms. So we'll shorten that. We can shorten that one of 2 ways. So we could call that either X+, which is very similar to C+, or we could draw a little 3-membered ring, which still has an X+. It looks just like that. Okay. Did I mention office hours today?
Yes.
12:30 to 1:30? and then I'm gone pretty much right at 1:30. So if you need help on homework, it's been due for a month. Today is not the day. All right. I love you guys, but all right. So our type 2 mechanism. All right. So let's talk about it. So what we've got is this is a trusty starting material. I really like this starting material. So let's draw it a little differently, though. All right. So this guy right here, it has a ring, and we have a tertiary carbon and a secondary carbon involved. All right, so again, we're going to have what we consider an electrophile-nucleophile combination, and so we'll go ahead and draw that out. So we've got electrophile, and we've got nucleophile. Now, what's different about this mechanism? Well, number one, our electrophile always has to have a lone pair. All right, so thus far, we've just seen hydrogens or protons act as our electrophile, and obviously that doesn't have a lone pair, so you never see a acid catalyzed reaction go through this mechanism. So the electrophile has a lone pair. Okay. So here we go. What do you think the first step of the reaction is going to be based on everything you know?
Deprotonate.
Well, we're not going to protonate because in this case we can't have the electrophile as a proton, but we are going to draw our arrow in the same way, right? This is all chemistry where we're going to take our negatively charged stuff and attach it to our positively charged stuff. And so if we were to think about the charges on our electrophile-nucleophile combo, if we were to put partial positives on this electrophile, this nucleophile, where would you put it, electrophile or nucleophile? What is going to be more attracted to electron density? Something that is positively charged or something that is negatively charged? Yeah, something that is positively charged. And so that's why every time we snap our electrons to the electrophile, we're doing so because the electrophile is an electrophile because it has a little bit of a partial positive charge. And so vice versa, the nucleophile must have what? Partial negative. Okay, so just like we've been attaching our double bond to our electrophile all along, we're going to do the same thing. All right, so we'll draw that in right there. And then what's going to happen to that bond between our electrophile and our nucleophile? Just like we've been doing. Yeah, it'll break. We'll just kick off our nucleophile. And so it goes away and does its own thing for a little while. All right, so here's the difference. So all along, what we've been doing is we've said, all right, we're going to attach our electrophile to our alkene, and we've got to pick which carbon it connects to. In this case, we don't have to do that because it connects to both. How does it connect to both? So what we're going to do is that lone pair, as all of this is going on, is going to snap the other carbon which is not connecting to our electrophile. So where would we start our arrow to show this? From the electrons always, and so specifically the lone pair on the electrophile. And we'll draw it right to that tertiary carbon, which would be the more stable carbocation, and so more likely would have more of an attraction to the electrophile anyway. All right, so what happens here? What we're going to end up with is two possibilities. Okay, so let's say this and so we're doing this thing all at once, right? We're forming our bond to the electrophile at the same time as we're using the lone pair of the electrophile to form this new red bond. And so do you think that could ever happen on different faces? Could we ever form basically a bond here to the electrophile on a wedge and a bond here on a dash at the same time? No, that's not going to happen. So every time we do this, we're going to add the electrophile to the same face on both carbons. And so what that means is if we attach from the front, we're going to have the electrophile on two wedges, just like that. So we'll have a positively charged E there because it's connected to two things now. Plus, we could also have attack from the back. And so in that case, our methyl will be pushed forward, and so our electrophile will be on two dashes. What's the relationship between those two things? Those are enantiomers. So you could just draw one and say plus enantiomer, right? I wouldn't know what you mean. Yeah.
What's the reason that the electrophile attaches to both again? I don't know this.
So, let's see. We can draw a picture. And so, let's think. So ultimately what we have is we have a picture that looks like this. So we have a double bond. So we'll draw a planar. So what that means is that we have p orbital there and p orbital there, right? So now we're going to attach an electrophile essentially to these p orbitals, right? And so what we end up with really is we're going to have something like this. Let's make this a methyl and this a methyl, so we're going to have regioselectivity. And so when we add our electrophile, what's going to happen is essentially we'll add our electrophile using one of those lobes, but now that electrophile, it's approaching from the top, right? And so if the electrophile, let's say we're going to snap the electrophile to this lobe right here. What lobe is going to be way easier on this carbon to connect to? Is it going to be the top one or the bottom one?
Top.
The top one. And so because of that, we're going to end up with this adding to the same face. And so if it attacks from one side, it's going to be on two wedges. If it attacks from the bottom side, it's going to be on two dashes. It's got to attack from the same side. So let's write that as a rule. Electrophile must add to same side of alkene. Would you specify that as a cis addition or a trans addition?
Cis.
Yeah, that's going to be a cis addition. We must have a cis addition in this first step for our electrophile adding to our alkenes. Sarah?
What does that have to do with the lone pair?
So essentially, we'll see that. We'll take a look at that in a sec. Yeah.
So basically, the electrophile attaches to both carbons that are part of the double bond.
Yep, it attaches at the same time, right? And so since there's only two electrons involved in that double bond, they can reach out and form a new bond. That's why we have to have that extra lone pair on the electrophile. We have to be able to form another bond, and so we have to have the electrons coming from somewhere. In this case, they're coming from the electrophile itself. Okay, so let's see, where are we at? Okay, so we've got our intermediates here. So what we need to do is, of course, our nucleophile went out into the wild. And so at this point, all right, so we have a positively charged thing and a negatively charged thing. What do you think is going to happen?
Snap.
They're going to snap together. Now, do you think that you're going to add the nucleophile to the E+? If we were to do so, what kind of charge would the E+ end up with?
2+, it's got a full count.
Oh, I guess it depends on the electrophile. Let's ignore that question for a second. I'm just going to tell you.
Neutral?
I guess in this case, but then we've got to consider whether we can break the octet rule in some cases. So we'll just forget that. What instead we'll say is that the nucleophile will snap to a carbon. We're always going to be attaching things to carbons. And so what we're going to end up with in every case, one of these electrophilic addition reactions, we're going to attach an electrophile to a carbon, and then to the other carbon we'll attach the nucleophile. Okay, so then the question is begged, which carbon are we going to connect the nucleophile to? And so let's think about this, this intermediate right here. So let's call this thing, all right, so we'll call this topic regioselectivity. And let's think about our intermediate. So our intermediate looks something like this. We'll see what it is. All right, so we're going to ignore stereochemistry when we're talking about regioselectivity, just complications we don't care about. All right, so we've got an E+, and now what we've really got is we're going to have this thing, and it is going to be in equilibrium with a couple of different intermediates. And so what can happen is we could have this process, and so in this process, what we would end up with is a structure that looks like this and leaves a positive charge there, right? So essentially that's going to be in equilibrium with this carbocation. We're simply breaking one of those bonds, leaving the carbon deficient. Of course, we could go the other way, right? We could snap the other carbon E bond. And so if we were to do that, we're essentially going to end up with this structure right here. Okay, so we've got basically three things in equilibrium here whenever we form one of these halonium intermediates. So first off, of these three, what's the most stable? Which one's closed shell?
The middle one?
The middle one, right? And so this is closed shell and most stable. But it doesn't help us figure out which is going to be the more positively charged carbon, right? Because we're snapping a nucleophile, something that's negatively charged. And so essentially, what's going to happen is that nucleophile being negatively charged is going to be more attracted to a carbon that has more positive density. All right, so let's compare the left side and the right side. Which is going to make a greater contribution, right? Which is going to exist more? Because we're talking about equilibria, not resonance structures, right? And so we're actually saying these things exist at some given time. And so what's going to exist more? Is it going to be this one or this one?
Blue.
Why the blue one?
More stable.
It's more stable. It's tertiary, right? And so what we can say is that this is the more stable C+, and so this would be the less stable C+. And so that gives us a big hint as to where we're going to end up attaching our nucleophile, because as we go back up to our mechanism, and if we were to indicate between these two carbons, the top one and the bottom one, which one has more of a partial positive charge, what would you say? Would it be the tertiary or the secondary? Tertiary. It'd be the tertiary, and it's the tertiary because this is going to be more stable, and so we're going to have a little bit more of this than we ever had of this. And so what we would say is we've got a partial positive here. We'll draw it. I'm going to draw it in the ring. So partial positive. So that means we've got a partial negative on the bottom. Okay, so finally, when we snap our nucleophile to one of the carbons, which is it going to be, the tertiary or the secondary? It's going to be the tertiary in both cases. Okay, so we're going to attach our carbon to the tertiary. And so ultimately, for regioselectivity, we want to ask ourselves which carbon would be a more stable carbocation. Okay, and so furthermore, thinking about how we've snapped together our carbocation mechanisms, would we call this Markovnikov or anti-Markovnikov? It's still Markovnikov, right? So what we see is that type 1 mechanisms have Markovnikov regioselectivity. Type 2 mechanisms have Markovnikov regioselectivity. It's the same in both cases. All right, so this is going to be actually we'll go up here and write it. Markovnikov. All right, so that's going to be our regioselectivity, but we also have to consider, I'm running out of space. All right, so we also have to consider stereoselectivity. So we'll also have a box here, stereoselectivity. All right, so in terms of stereoselectivity, this was pretty easy to remember. So we know which carbon we're going to attack, and so the resulting phrase has been a joke on the back of chemistry club t-shirts for decades around the country. All you want to remember is the idea of a backside attack. All right, so we want to remember backside attack, and so what that means is that when we go back up here and we think about our nucleophile approaching our carbon, compared to the electrophile, it's going to approach that carbon from the backside. It's going to be the backside from that electrophile. And so if our electrophile is on a wedge on this top picture, when the nucleophile comes in, is it going to approach from the front or from the back? Backside. It's going to approach from the back, right? The backside of the electrophile. And so what happens is when we draw our product, what we'll end up with is this stereocenter here. Is that going to change at all? We're not doing any chemistry there, right? We're going to keep our electrophile connected there. So we end up with our electrophile on a wedge. And so what we want to show is essentially our nucleophile is displacing our electrophile from its backside. And so the nucleophile, is it going to end up on a wedge or a dash? Which face is it approaching from? Front face or back face? Back face, which means it's going to be on a dash. And so that's exactly what we see. So here we've got our nucleophile. What's happened to our methyl group? It's been pushed forward onto a wedge. All right, and so vice versa, for our other enantiomer of the halonium ion, since our electrophile in that case is on a dash, is our nucleophile going to attack this carbon from the front or the back? What's the backside of a dash? It's the front face, right? It's the wedge. And so our nucleophile in this case, in this product, will be on this carbon as a wedge or a dash. It's going to be a wedge. And so what do these two things have in common in terms of stereoselectivity? Are they syn or are they anti? Do we end up with the electrophile and the nucleophile on the same face or on opposite faces? Opposite faces, syn or anti? Anti. All right, so in this case, when we talk about stereoselectivity, what we have is anti. All right, let's box those in. All right, so is that going to arise more, or are we going to have more products formed from this compared to a carbocation reaction or less products? We should have less products, right? Because unlike the carbocation mechanisms that have no stereoselectivity, you get syn and anti-addition. In this case, you're only ever going to see the anti-addition. All right, so that's it. That's the mechanism. So let's look at some examples. Well, we got time for one example, I guess. All right. So we'll call this Roman numeral number 6, and so we'll just say X plus reaction. This is going to be our halonium reaction. So reaction is going to be, this is 3. Reaction number 3, we're going to call a halogenation. And so we're going to treat our double bond alkene with what kind of reagent do you think? A halogen, right? It's in the name. It's a halogenation. And so what this is we'll start with our trusty starting material. For example, what we're going to use is something like Br2, dibromine. All right, and so we look at that bond and we think, well, that's not going to be a polar bond, right? How on earth is one of these going to be partial negative, partial positive? Why would this happen in the first place? But bromine, being pretty far down the periodic table, is fairly big. And because it's fairly big, what we have is kind of a temporary dipole buildup, right? We're going to have these things that are big and they're relatively easily polarizable. And so at any given instant, what you can have is a partial positive on one end and a partial negative on the other end. So now that we've got a little bit of charge build up in one of these bromines, do we have a reason for a reaction to occur? Yeah, sure. We've got electron density that wants that, and so we end up drawing an arrow there. And so that's going to kick off the other bromine. But unlike a carbocation mechanism, what else is going to happen? One of those lone pairs from the initial bromine will what? It'll snap back onto the alkene at the same time. And so what we see is something that looks like this. So we end up with an intermediate. And so this initial addition, is the bromine going to end up on the same face or on opposite faces of that double bond? Same face, right? It's got to add to the same face. And so we could have the methyl pushed back, which would give us our bromine on a wedge here and also on a wedge here. And then furthermore, we would say plus enantiomer, right? Because we could also have that bromine add from the back face and have the enantiomer of this picture. All right, so then what we've got left over is we've got a bromide ion floating around in solution. And so do we have something negative and positive that we could snap together? Yep, definitely. And so are we going to snap the bromines together, or are we going to snap a bromine to a carbon? Snap it to a carbon. Which one, the tertiary or the secondary carbon? Tertiary, because this reaction shows Markovnikov addition. And so finally, when we add it to that tertiary carbon, the structure drawn, will it approach from the front or the back? It'll draw from the, yeah, what you said. It'll approach from the back. And so in this case, what we get is our anti-addition. And so our methyl gets pushed up to a wedge. Our new bromine is on a dash. Our old bromine is still on a wedge. And so what we see is this, of course, it's this plus enantiomer, right? Because using the enantiomer right here, we're going to follow the same rules. It's going to be Markovnikov addition, and you're going to get the anti. And so what we'll end up with in that case is this would be on a dash, and this would be on a wedge. All right, let's quickly add this to our table and call it a day. So this is going to be reaction number 3. Our electrophile in this case is what? It's just a halogen, right? And so the nucleophile is what? It's another halogen. So in this case, we're just adding a couple of X's to our double bond. And so the reagents you'll see, Br2 will do this reaction. And so will dichlorine, but that's pretty much the only two. All right, so anytime you see dichlorine and dibromine, you know you're going to undergo a halogenation like this. Regioselectivity, Markovnikov or anti-Markovnikov?
Markovnikov.
We know the mechanism is Markovnikov, but we're going to make it even easier. Since these things are going to end up symmetrical, do we really even have any regiochemistry? Not really, right? Because what if we flipped these two bromines? We kept the stereochemistry the same, but we have a different product? It'd be the same exact product, right? We'd just be swapping bromines. In this case, we don't even have to worry about regiochemistry. So we have none regio selectivity. I think, none. There's nothing there. That's a no. No regio selectivity. If you told me that this reaction is Markovnikov, that's fine. I understand what you mean, right? It goes through a Markovnikov type mechanism, but at the end, when we look at the product, you couldn't prove it to me, right? And so we would just say, well, it doesn't matter. The symmetry of the BR2 makes it easy. Stereoselectivity, sen or anti? Anti. And so mechanism sign.
2 plus.
You can see X plus, or if you like, you can draw the three-membered ring, and it looks like that. All right, have a great weekend. No workshop on Sunday.
So earlier on, why is water more nucleophilic than the?
So basicity and nucleophilicity are very similar.
Okay.
And so if we think about H2O
Yeah.
and HBr. All right,
Yeah.
so essentially what we're doing is let's see if I can, all right, actually, we want to compare bases. And so what we want to do to compare bases is we want to look at the acid stream. So we know the bases we're comparing are H2O and Br minus.
Yeah.
All right, so which is a stronger acid, HBr or H2O?
HBr.
Yeah, so this is stronger acid, and so that means what's a stronger base, H2O or Br minus?
H2O.
So this is a stronger base.
And
So since basicity and nucleophilicity are very closely related, it ends up being the H2O.
Okay, cool, thanks.
Okay, I have 2 questions. First of all, why was there a difference of charges on the two bromines that were connected again?
Didn't understand.
We had like the dibromide.
It's just a temporary polarization. Nothing more. So there's not, you can't draw a dipole, but what you can say is these electrons, they do
just
have
move
movement.
around.
And at any given time, what you might find is one of the bromines might be slightly more positively charged.
Okay,
So
and then why is there no regioselectivity on this reaction?
So it goes through a Markovnikov type addition, but in the end, we have a
Same
bromine on the
bromine.
top one and a bromine on the bottom one, and so there's really no way to tell the difference between what we've added, right? Because it's the same thing.
And how does that differ from the other regios?
Well, so before we were adding like HBr, where clearly there are 2 different things we're adding. Right, so instead of adding a proton down here, what we have is just another bromine. And again,
Oh, so the other one's regioselectivity was saying which carbon are you going to add the H2, which carbon are you going to add the other halogen?
right, but in this case,
But
since
here
we
it's
end
the
up
same
with,
thing.
it's the same thing, so it's, we
Okay.
can't, we know mechanistically how it gets there, but if you were to ask someone the regiochemistry, it's like saying, well, there's no regioisomers because there's no possibility of them forming because it's the same thing.
Okay.
So,
And then in terms of like the chapters that we're going to cover for the test,
Yeah.
do you know like what will be the last one?
we won't get out of 6. I
We
hope
won't.
to get be done with 6.
So
basically.
don't read 12 or 13 until the test. Don't even.
Oh yeah, definitely don't do that.